Okay, we have these two spherical conducting shells. They are concentric, they have the same common center. The inner conducting shell, spherical shell, has a radius a and charge of 2q. The outer conducting shell has a radius of 2a with charge of q. So the first question is, one is labeling the inner spherical shell and two labeling the outer spherical shell. What is the difference between the potentials of the inner shell and the outer shell when we have these charge distribution uniformly distributed over the metal surfaces? The second question is the same potential difference, this time when the outer shell is grounded. Okay, so we will ground, in the second case we will ground the outer shell, and let's and we will calculate the potential difference again. Okay, but this is the second question. The third question is the same potential difference, but this time the inner shell is grounded. Okay, so let's start with the first case, that these two shells are not grounded, they are isolated from universe, no any connections with nothing. We have the inner shell having the total charge q, the outer shell having the total charge q. What is the difference between the potential of the inner shell and the outer shell? So we know that this potential difference is related to the electric field in between the shells by this equation, minus 1, 2, the electric field in this region between these two shells, E dot dr. So this is the starting point, and of course to calculate this potential difference we should know what the electric field between the inner shell and the outer shell, this region where the radius is between a and 2a. But you know, it is very easy to express this electric field by just using the Gauss's law. Take any point in between these two shells and draw an imaginary Gaussian surface and calculate the flux, and this flux should be equal to the total charge inside this imaginary Gaussian surface. In this case it will be just 2q. So what you will have is the electric field between the regions k times the inner charge, which is 2q, divided by r square, and this is q. So this is the electric field between the inner shell and the outer shell, between the shell number 1 and number 2, and we just put this into this integral to calculate the potential difference. Okay, let's continue over here. Well, these limits of the integration in fact are the radii of the second shell and the first shell. So just put these minus the radius of second shell is 2a and the first shell is a, and k times 2q divided by r square dr. Okay, so the top are, you know, constants, can be taken outside the integral, and 1 over r square integral is just minus 1 over r. So the result, I'm just writing over here, v2 minus v1 minus 2kq, okay, multiplied by minus 1 over r. This is the result of integration from a to 2a. Well, evaluated at these radii, we will have 2 times q times a, 1 over a minus 1 over 2a, and 2 over 2a minus 1 over 2a makes 1 over 2a, multiplied by 2 times kq, you got k times q divided by a. So this is the result, that the potential difference between the inner shell and the outer shell, where the inner shell have the total net charge of 2q and the outer shell has the total net charge of q. Alright, so the second part of our question. Again, we will calculate the same potential difference. I do not this time the potential difference as primes because the conditions of the second case is different compared to the first case. In the second case, we will now ground the second shell, the outer shell. That means we will keep the second shell at zero potential. Okay, grounding means always, whenever any conductor is grounded, that means this conductor is at zero potential. So of course, since now the second shell has a connection to the ground, its charge will be different. But will it make any difference? I mean, having a different charge of the outer shell make any difference between the potential difference? Let's see. Well, this time again we will calculate the potential difference. Now I'm denoting the primes with the same expression 1, 2 and E dot dr. Okay, let's consider now what will be the electric field, or will electric field change in between these shells when you ground the outer shell. But the thing is, right away I can say that this will not make any difference for the electric field, because once again, you pick up any point in between and draw a Gaussian surface and calculate the flux and just look at the total charge inside, which does not change in the second case because the inner shell is still isolated. The electric field will be the same. Okay, the electric field will be the same expression which was indicated in the previous case. Even if you ground the outer shell, the electric field doesn't change. So if the electric field doesn't change, it's the same, then why should this potential difference change? Of course it will not change. It will be equal to V1 minus V2, which is just the previous case, and do the same calculations with the same electric field, so you get the same expression, KQ divided by A. Okay, what next? What next is, again, we will calculate the same potential difference. Well, not the same, maybe. We will calculate the potential difference again between these two conducting spheres. Initially, they were, of charge 2q and q. But this time, I make the inner shell grounded. That means I just keep the potential of the inner shell, V1, at 0. Okay. So, again, since you have a connection to the ground now, initially you had a charge of 2q, net charge of 2q on the inner shell. Once you make this connection to the ground, this 2q will change. Okay. But how will it change? It will change, and this change will affect our results now, because this change in the electric charge in the inner shell will change the electric field in between the shells, in the region between the shells. Alright, so this time V1 double prime and minus V2 double prime will not be equal to the potential difference which is what in the previous cases. Why it will be different? Because the inner shell now will have a different charge. Okay, so let's look at the picture. Then in this case, let me just erase the initial charge, which was 2q. Okay, now since it is grounded, its charge will change, but we don't know what this charge is. Let's put this charge Q prime. Okay, we don't know what this charge is. We have to know what this charge is because, you know, we will calculate this potential difference, and to calculate the potential difference between these two shells, we need the electric field in between this region, and in order to you know, use the electric field expressions in this region, we have to know what the charge of the inner shell is. That's why, you know, we have to calculate in this new situation, we have to calculate the let's say the charge, new induced charge on the inner shell. How can we find this? So I will make a trick at this point, okay? And since one thing, since we know that you know, the potential of the inner shell is at zero potential, and the outer shell has still this net charge of Q, and also I know the potential at infinity, very far distance from these two spheres. We know that the potential at the infinity is also zero. Okay, the potential at the infinity is also zero. So how will I calculate this Q prime? Just watch me. Okay, so for this I just, you know, want to calculate the potential difference between the inner shell and any point at the infinity. Okay, so you will see that, I mean, you may say that, well, what you write here is very trivial because v1 double prime, well, let me put double prime in over here because this is the third case. v1 double prime is already zero and v infinity is already zero, so 0 minus 0 gives you nothing. But wait a second over here. What is this potential difference? With this potential difference, according to the you know, definition of the potential difference, is nothing but this electric field integral between the radius of the inner shell A and infinity. Okay, so let's reverse this integral from 1 to infinity. Well, 1 is just r is equal to A, which is the inner shell radius, from A to infinity. But the thing is, you know, since while going from r is equal to A from the surface of the inner shell to infinity, I cross a border. I cross a region where, you know, there might be some change. So I have to, you know, I have to divide this integral into two pieces. Let's first run this integral from A to 2A, from here to here, from the surface of the inner shell to the surface of the outer shell, E dot dr, plus from 2A to infinity, again, E dot dr. All right. Okay, so now you will see that this right-hand side, the right-hand side equation, will contain some charges, the charge of inner shell and the outer shell, and I already know that the left-hand side of this equation is equal to 0. Okay, this is 0 because v double prime is 0, v1 double prime is 0, and v infinity is 0. But, you know, this will give me an equation, and this equation, when it's solved for the sake of Q prime, for the sake of the new charge distribution of the inner shell, I will be able to express this Q prime in terms of the charge of the outer shell. So let's see. What is the electric field in the region between inner shell and the outer shell? It's nothing but KQ prime divided by R squared. So this electric field over here, I will just continue in the second line. Okay, from A to 2A, it is K Q prime divided by r square dr plus the electric field in the region where r, the radius, is larger than 2a. So this depends on the total charge of the inner shell and the outer shell, because for any point outside the outer shell, pick up any point at the outer shell and draw an imaginary Gaussian surface and calculate the flux, and this flux will be equal to the total charge which resides inside this imaginary Gaussian surface, which is nothing but q prime plus q. So that means the electric field where r is larger than 2a is nothing but, let me write first the integral 2a to infinity, k q plus q prime divided by r square dr. Okay, now I'm just one step closer to the final result. So what is this will give to me? It is 1 over minus 1 over r integral minus 1 over r k q prime minus 1 over r 1 over a minus 1 over 2a. Okay, this is the result of the first integral, plus, and this is again will give me minus 1 over r integral. Minus 1 over r integral is one from to be evaluated at these limits, 1 over 2a minus 1 over infinity. So k q plus q prime multiplied by 1 over 2a. Okay, I'm not very explicitly writing these integrations because they are easy and you can handle this anyway. So on the right hand side, what do we have? K q prime multiplied by minus 1 over 2a. Again, I have the same expression, k q prime 1 over 2a. So these will go away. This term and this term will go away. What I'm left with, k q prime multiplied by 1 over a plus k q multiplied by 1 over 2a. So k q prime in k parenthesis q prime divided by a, let me write this a distinct from q. My letter q and a looks like the same, but I just let me erase this, I messed it up. Q prime divided by a. So the second term is plus 1 over q multiplied by 1 over 2a, and this whole expression is equal to 0 because this potential difference is 0 anyway, and this will give me q prime when the inner shell is grounded. When the inner shell is grounded, the charge it will obtain from the ground will be, in terms of the charge of the outer shell, minus q divided by 2. Okay, so this is the result. Once you ground the inner shell was originally having a charge of 2q plus 2q, but once you ground this with the presence of the outer shell with a charge of q, it will make a new charge for the inner shell, and this new charge for the inner shell will be just half of the charge of outer shell with a minus sign. Okay, so what next? What next is I will calculate this potential difference, where in that case the inner shell has a charge of minus q over 2 and the outer shell has a charge of q, and the potential difference between these two. now I can calculate the electric field in between these two shells because I know what the charge is for the inner shell. It is just minus Q divided by 2. Okay. So let me erase these parts and make this double primes from 2 to 1 E dot dr. Okay, since now I have a charge of minus Q over 2, the electric field in between the region has this. I only write down the magnitude K Q over 2 divided by 1 over R square. Well, I should put minus sign here with this unit vector, because now since the inner shell has a negative charge, the electric field lines will be inward to the surface of the inner shell. So once you put this value on the integral, you get from 2 to 1 K Q divided by 2 R square dr. In fact, 2 is 2a and 1 is a, because the limits of the integration is in terms of r. So I got k q divided by 2, okay, and the result of the integration is 1 over r to be run from evaluated at the points a and 2a. This makes the result kq divided by 2 1 over 2a minus 1 over a, and you got, when you solve this, minus 1 over 2a minus kq divided by 4a. Okay, if I'm not wrong, let me check. This is 2 over 2a. That makes this 1 over minus 1 over 2a multiplied by this, yeah. So this is now the same, the new potential difference between the shells in the case that the inner shell is grounded. Okay, so it is different than kq divided by a. Kq divided by a was the answer for the first two questions, but now the last question it is different because this time the inner shell is grounded and the outer shell is at its original charge. Okay, so this ends the solution of this problem, finding the potential differences between two charged shells in case of different grounding scenarios.